right. All right, let's restart. So I think the property for the Lebesgue-Stieltjes integral, which you usually you don't show, is the finite variation part, because you don't care. And I mean, all the other properties are the standard things you expect from an integral to hold, right? So the associativity, if you integrate h with respect to an integral of f with respect to a, it's the same as the integral of h multiplied with f, and then the integral with respect to a. Integration by parts is, I mean, what we called in the lecture product rule. So if you integrate a with respect to b, and both are functions of finite variation, then you can swap the order of the integration. So this is the same as the product of a multiplied with b at time t minus the product at time 0, and then minus the integral now at b with respect to a. So you can interchange the order, I mean, the integration, and then you have the chain rule. So if you apply f with respect a function which is here in C1, you apply it to the finite variation process t, then you can write it as an integral starting from the initial point, and then the integral of f applied to a with respect to a, right? And just to me, if you have a general semi-martingale, what you see is, and this is what we talk more about next week, you have the second order corrector term. And here, two things. I mean, this is of course completely consistent with the Ito integral, right? Because you have a finite variation process, so the quadratic variation is 0, so the second order corrector disappears. And the second thing you see here, if you apply a function of in C1 to a finite variation process, it's again a finite variation, because we already have seen, or just have seen, that this term here is of finite variation. Okay. So this is, I mean, questions? Okay. All right. So, well, this is, I mean, this is not the, I mean, if you want to show this property 4 and 5, I mean, the usual way is of course completely different, but for us, I mean, just apply Ito's formula. And this here is, okay, you do the standard way of first showing it for simple function, for simple indicator function, and then you extend it by a monotone class argument. Okay. So what we want to do now is we want to apply this deterministic classical analysis theory to a stochastic process of finite variation. So that's actually what we have. And that was a bit unprecise in the lecture. So let me correct it a bit and restrict the class of integrand. So what we want to have, that our integrand is, I mean, we had always this predictability assumption, which we need for the integral with respect to the martingale. And now we want to put the extra assumption that the process is locally bounded. So locally bounded means, okay, you can find a sequence of constants and a localizing sequence. So meaning this sequence almost surely goes to t, so the terminal time.
Sorry to interrupt.
Sorry, I don't understand the monotone class argument you mentioned. I don't understand
it. Okay. This is a bit outside the lecture. So I mean, what you probably have seen is, if you want to prove such an equation, is that you first start proving it for elementary function, right? Where is this? So functions which basically look like, so h is equal to, let's make it as simple as possible by x Right? So if you prove the identity for this function, this is here, it's not called as a small h. And the same for so the second function was f, and this is ab, right? So you take the most simple class of function you can think of, and these are just indicator functions. And then you show so you just plug in the definitions. So because if you take these simple functions, all the integrals are just sums. So classical finite sums. And this means then you can just rearrange the sums and you get this equation. Right? And then you need to have an extension argument which tells you, well, if I can do this, then I can also do simple ones, right? And also holds for function which are h t. I used the different notation. So then you want to consider what we call elementary functions, meaning you sum up some n, and then you have here some nice value. ti plus 1. This is fun. Right. So this is the next step you do. So if you know you have the associativity for the simple step function, you consider functions of the form that you have basically a step function. These are just some constants, dhn. And then you apply, you know the associativity holds for this function, so you have it also for such function h and f. And then these functions are basically dense. So what you want to extend it to the class of all Borel measurable function. And one argument is, one of these extension arguments is called monotone class theorem. You might have called it differently in your analysis course, but basically what you need to have a general convergence argument, which tells you if it holds for such elementary processes, then you can, under certain condition, extend it to all Borel measurable functions. Is this good enough?
Are the lectures from the, the document AMF tutorial going to be uploaded to the homepage?
Yes, what you see in the end is the full, okay, now I killed it. Where's the issue? Yes, usually if there's no error, which I'm not going to find now, there's a PDF file. Well, usually what you have, if you look at the lecture notes, they should not be broken. You can, right, you have these looks is just, this is just a LaTeX file you see here, and then you can generate, as usual, your PDF file. And what I will give you afterwards is the PDF file.
Okay, thank you.
But now, I don't know why. Probably this is my issue. Okay, no. Okay, I will need a few minutes to find the error which I created. Right. So this is how you do it, and this is, you have seen in some way already in some course. So this is, I don't want to spend too much time on it because this is not the main point. The main point is everything works nicely. All right. So
sorry, before we go on, could you also show property 5 again?
You mean this one?
Yes. Is the integrand really f and not the derivative of f?
Oh, good point. Yeah, sorry. Yeah, I mean, otherwise it would be not consistent with our E2 formula, right? So thank you very much. This is just a typo, which probably also exists in the lecture notes. Okay. And now we want to apply this theory, I mean this deterministic theory to our predictable integrand H, right? So this is at the beginning what we wanted to do is we wanted to define this. And if you recall, then you realize, okay, here we need to have some predictability of the integrand. So let us restrict to, sorry. So what we do is we restrict the class of predictive integrands to what's called locally bounded ones. Locally bounded means we have a sequence of constant and a localizing sequence of stopping time. So they are converging if n goes to infinity to the terminal time capital T. And if we stop this integrand H, so this predictable process, it's bounded by the constant C. But the constant might blow up to infinity, which is not an issue, as long as for every localizing sequence, for every localizing stopping time, this is a finite object. And well, so this is just the set L infinity log is just the set of all predictable processes which are locally bounded. And you hope now, I hope now you all agree that with this class of integrands, you can define really for almost all omega, the integral of H, assuming it's in L infinity log with respect to A, and basically you can do it for almost all omega. So except the null set. And if you think about our standing assumption that all the null sets are F0 measurable, that's fine for us. So this is creates no measurability issues, right? So we define it, we localize now the integrand, and if T is in the interval 0 to tau n, then this is the integral, and for consistency reason, this is well posed. So that's the Lebesgue-Stieltjes integral we wanted to define for these processes here. So for the general integration theory of CB martingales. Okay. Okay. Right. This is the first ingredient, which I somehow always just used without properly going through it. But now you have it. And the second ingredient, and this is what we developed properly in the lecture already, is the what E2 integral or integration theory for continuous local martingales. So here, I mean, this is what we already have seen in the lecture. So there's not much to say. So if I have now a function in L2 with respect to M, then I will have this defining property of the martingale of the E2 integral. So this means that the quadratic covariation, so there exists a unique object, which is uniformly in L2, continuous, and starts at 0, which has the property that this element and the quadratic covariation with any other local martingale is equal to the integral of H with respect to the covariation process of M and N. Right, and this is what we call E2 integral and how we constructed it. And the usual writing is the integral form here. And what we also observe from basically from this construction is that this is in the end a very nice map. So this is a linear map. actually is even bilinear, so it's linear in H and M, and it's continuous and even isometry, basically saying that if you consider the L2 norm of the integral, it's equal to the L2 norm of the integrand with respect to this product measure generated by the probability measure and the quadratic variation term. Okay, and this is called E2 isometry. And then we can extend it to the actual class we considered. So if I have a continuous local martingale, and then I can integral all function which I can localize. So I find a localizing sequence as before, such that the localized integrands are in L2. And then we define the integral to be, well, H against M is just the integral of the localized integrands if t is in the interval 0 to t, and this is consistent by the uniqueness properties here by this uniqueness property.
Hello, I'm sorry for speaking in, but one of the course participants texted me on WhatsApp and said that the platform threw him out, and now the link that you sent, like the new link that you sent per email, is no longer functioning with him. And he asked me on WhatsApp to tell you.
That's good. I'm of course not an expert, so I'm using it the first time today. Any recommendation from your side?
Maybe we can open a new room with a new link. Like, I don't know.
but I see all participants are still here. So, I mean, if I understood it right, we were 13 participants and we are still 13 participants. So my guess is that Zoom believes that he is still here. Or she.
No, I can see the list. He is definitely not on the list right now. I think we were just 14 before that, or shortly 14.
All right, then.
Professor Puma, what you can do is when you set up the meeting, there's I think there was a button that you can choose that the meeting number is always the same, so it's unique to you, and then we can just keep using it also.
Wait, what is the idea?
Before you set up, when you set up a meeting, there is an option of making this meeting, there's a meeting number, I believe. Yeah. That's unique to you, only to you, and then from there we don't have to, keep having a new meeting number.
So I can manage. I can invite people.
Oh yeah, that would work also.
Yeah, but I think I get then the same email. So then basically I get the meeting ID, the password, and I think this is exactly the same as before. I mean, like, let me send out the email. Maybe there's some changes. Wait. New email.
Okay, so I just tried joining from my phone and it still works. So maybe he or she should try the right link, or if his computer's set up the right way, or try it from their phone.
I'll let him know.
Okay, let's. Oh, I got a lot of Meeting ID is ungültig. Yeah, no. Okay. I mean, in the end, it's not super bad, right? Because all what I'm typing here or doing will be online. So yeah, let me know if it's not working in 5 minutes, then we can.
Okay, sure.
Okay, where do I share again? There. Okay. Okay. So this is the E2 integral we define, and now we put both ingredients together as our initial strategy was saying, and this is where I was a bit unprecise and I want to restrict the class of integrants a bit to make it clean, is so the class of integrants we are considering is Lx, which is the class which can be integrated with respect to M. So this is all the predictable processes which can be localized to BLL2. And I mean, this does not depend on H, right? This is the class of all predictable processes which are locally bounded, right? Then, I mean, this is fine. So if I have an integrand which is in Lx, then we can, as our planned strategy was, define the integral of H with respect to a semi-martingale. So,
and the locally bounded thing only applies to A, so the finite variation part, and the LM applies only to the martingale part, right?
Yes, but I mean, this is in this section, right? This is no, this intersection. You take the intersection of both things. So we consider only those predictable integrands. So wait, I can also write this out. So this is H in H. So H is predictable and locally.
Okay, also funktioniert jetzt bei mir übers Handy.
Läuft. Super. So this is also predictable integral such that, and now we take this one. Right?
Yeah, but H is a semi-martingale, right?
Sorry?
H is a semi-martingale, right?
H is not, no, H is a predictable process. This is our integrand.
Okay.
And X is the semi-martingale. This is.
Oh, okay. Okay, now get it. Okay.
It continues. Right. And I think this is what I already somewhere used because in my head it was clear, but in the lecture notes, probably not. So if then so this is the process in time is again a semi-martingale. And let's make this to a lemma. Where's lemma? Right? Oh, not all to a lemma. That's so I think this is not hard to see. Okay, because I mean we know if you have a Itro integral, so a stochastic integral with respect to a local martingale, it's again a local martingale. So okay, I will make it nice after the lecture. So right, if I have this object, this is a local martingale, this is of finite variation. So this gives me directly the classical, I mean, the definition of a semi-martingale into a local martingale part and a finite variation part. But this is somehow what we use rather often now, is that we can basically integrate with respect to a stochastic integral. And note this thing here is also called right. This is a bit unfair, right? Because the half of it is just the classical Lebesgue-Stieltjes integral, but I mean, this is probably just being lazy saying, okay, this is just the E2 integral. But I mean, this is actually where you need to have the characteristic construction, and this is where you can use classical analysis, and then you put it together to have the characteristic integral, or E2 integral. But also what you see on the exercise sheet is, I mean, there are different types of characteristic integrals. So this is why I'm careful not to call it too often characteristic integral, because it's the one specific to E2. Okay, are there questions? Anyone? If not, I would come now to the solutions to problem sheet 4. So since we have not too much time left for today, is there a priority which one you would see? I mean, the solutions are online anyway already, but if you say, okay, you want to, I think there are 3 exercises this time. So if you have a priority, which one you would like to discuss first, please, well, write it now in the chat. Then we can I see where I want to start? Where there's something going on. 2, 3, 2.
One more question regarding the lecture.
Yes.
So as it stands right now, we're only gonna meet up on Thursdays for a half recap of lecture and one half basically tutorial.
This is this is the session for today. So my plan is for next week to do basically, I assume that you always have time, all the sessions, all the 3 sessions, and I would like to do them all. We might do only 2 sessions if I realize so I have an idea what I want to do per week. If I'm much faster because I don't need to write at the blackboard anymore, then we might downscale it to 2 sessions. But this is on how high the demand is. So I really want to do the same amount as usual. But usually, I mean, you see here, I mean, if I go through my notes, I can be really fast. Okay, other questions? Okay, now I have like a draw, so 2 and 3. So, okay, we start with 2 because we need to have 2 done in order to do 3. And probably next week we start with 3. So this means, so I want to do next week on, so to get into normal schedule again, I start with Tuesday morning with the similar session than today. So half a lecture, half a tutorial. Then probably do the normal tutorial, and then we start doing normal lectures on Thursday again. And I mean, I will still keep updating a bit the lecture notes so that you can familiarize yourself with the content. So I will go over all the things I have written there already once more so that you can also ask questions. But I mean, I might be a bit fast, so please read it before the lecture so that, you know, you're not getting lost during the Zoom sessions here. All right. Small request. Yeah, okay, yeah, I could do this, but I also don't want that, I mean, people get lost by seeing too many information. So I try to optimize it along the way. All right, so we have, let's go back to the screen and start with 2. So, I mean, if you want to, you can already open so So this is 2, right? It's like a cooking show. I have prepared some stuff. So that's what we want to do. And well, I have a proof environment here. And you can, well, I mean, as I said, you can open already the sample solutions. I've probably downloaded on my homepage and then, well, have a look there already. So first thing we want, so with the assumption we have here, so what we want to do, okay, let me recall it first. So we have a continuous martingale. So to make our life easier, we are not considering general semi-martingales starting at 0 as before. We have a sequence of L2 integrable integrants. So these are predictable integrants, which are L in L2 with respect to the product measure generated by M. And we have function H in a L2FM. So this is dominating the sequence and it's bounded itself. Well, for almost all elements in the product space. And what we want to show is if these functions Hn goes to 0 pointwise, then the limit of probability of the supremum. So basically we have that the integral process goes to 0 uniformly in time in probability. Right? So this is somehow, I mean, this is the limit in probability and this is just written it out again so that you see. And of course, if we have the limit in probability goes to 0, then we can find a subsequence that it goes almost surely to 0. Okay, so the assumption is this, right? That's what we have. I'll make it shorter, so pointwise. The main point here is we have it pointwise. Let's forget about all these other things. I mean, I wrote the thing a bit more precise on the. So this is what we have, and the first thing we want to have somehow that we go, because if we want to talk about integration here, we want to talk about limits in L2, because there we have all the estimates. So first thing we want to do is we want to go from pointwise conversion to L2 convergence, and well, we use the obvious thing that we know that these Hn are bounded by a function H, and well, the absolute values of H is also bounded. Yes, bounded. So, I mean, why do I want to have everything bounded is because I want to use dominated conversion. Right. So this means I have this limit here in L2. Now stop me if you disagree, because what does it mean here is, well, that the integral, okay, let's make it of 0 to t of, okay, I have here my integrants, h and t, and well, I have an L2 norm, so I have the squares around it. And then I have the product space, so I have the product measure. Let's make it to 0 as n goes to infinity. Right, this is the definition. And the point by dominated conversion is I know that these go pointwise to 0 and they are dominated by H, so I can interchange by dominated conversion the limits, so this goes to 0 as well. Okay. And what we also note that if we consider now this integral process from 0 to t of hn, okay, you wanted to see a bit more, and you integrate it with respect to m, is a continuous martingale, right? Okay, so what can we do now? So we know that if we consider here the expected value of the supremum for 0 to t, and this is well in L2 actually, so I can put this here in, and I want to consider the L2 norm of this. How can we estimate this? Okay, this is so you want to use Doob's inequality. So what I can use here, Doob, means I have a constant which depends on p, and p is actually 2. And then I can estimate, as it's a martingale, right? This is why I wanted to observe that this here is a martingale. I can estimate this supremum with the terminal time. Can I also, no, that's not, this is, right, this is here, Doob's maximal. Right. So this is Doob's maximal equality. Because I have a martingale, I can estimate the running maximum to the power 2 by the terminal value to the power 2. And now, well, this is a martingale, so there's no semi-martingale property. So I look at the properties of the martingale here, and this is now I have E2 isometry telling me this is nothing else than this term here. So this is actually equality here. So I have C2 of this, and now I have here, of course, an n, and then the power 2. Right. So that's nice. So here I use E2. Okay. Well, and now I look at my L2 conversion here. So this term appears here, and I know that this term goes to 0 by assumption. So, oh, it's not. So this goes to 0 as n. Right, okay, this is and this is by this property here. Do I want to label it? No, okay. And well, since this is bound, I mean, this is a positive thing here, right? So this is a primum over the squares. This is always positive. So this is sandwiched by 0, and then it goes to 0 again. So, and we get this object here goes to 0 as n goes to as, that's here, this is also missing, right? And to infinity. And okay, in which norm? Well, in the L2 norm of, well, with respect to probability measure, right? So, I mean, this is here just an L2 random variable, and you take the square. So this is, I think Paul was complaining about this, but this is the same as this. All right, so this is, I mean, just an L2 random variable, which goes to 0 in L2, right? This is what we show here. And now, well, we know that L2 conversion implies right at. So L2 conversion leads to convergence in probability. So let's take this, put it here, and make it in probability. Right. And that's already what we wanted to show. Going back to the exercise here, that's exactly what we wanted to show. Okay, let me. Does anyone know how I can share my screen and still see the chat? So are there questions concerning this exercise here? Stop sharing, which is probably, you know, there are no questions. Are there questions? Is still someone here?
Yes. Yes.
Yes.
Okay. Good. All right. I mean, so this is a nice exercise because, okay, you mean at this point in the lecture, the only theorem you could use for all the three questions is this here. I mean, this is all the properties we had at this point. And so the purpose of all these three exercises were for you to practice applying this theory. And this is actually what we have done here. So, okay, you need to know that you want to go from pointwise conversion to L2 convergence, but this is why there was the extra assumption of having some bound. So you can use domination conversion to do this, and then you use the martingale property, right? This is in here. Well, sorry. I mean, it's a bit hidden, but this is saying, okay, if I have an intrinsic integral, then I know it's a martingale again. So I can do Stoops inequality, and then, okay, I have the Ito isometry, and here we are. We can apply the conversion that it goes to 0 to get that this term goes to L2. And then my standard argument, L2 convergence implies convergence in probability. Okay, so I think it's enough for today. If you have no question, I would stop the session here and then start doing on Tuesday the exercise 3 and talk about Ito's formula and the exercise sheet 5, because then we have a clean cut, and then we go over to the mathematical finance part. So I think it makes sense to first really finish now the stochastic integration part, and then starting on Tuesday afternoon, which is usually a tutorial, but then we do a lecture going through the finance stuff. I already started in the lecture notes, and I will update the lecture notes a bit today or tomorrow, probably by only 1 page, because, well, we have done already a lot, but since I want to have so if you want to cover certain material, I want to update it anyway. All right, are there questions from your side?
No.
So if nobody else has a question, I want to discuss my problem, this technical thing, because I can't use Zoom on my PC anymore. Yeah, that's a big problem, because on my handy smartphone it's so small. So
I have no idea.
Why can't you use it anymore?
Yeah,